last class we saw how we can synthesize the basic structure required for an operational voltage amplifier starting from the fundamentals. Ideal voltage controlled voltage source G matrix is defined with these elements being 0 and only the forward transfer parameter being finite. And this finite forward transfer parameter in the case of operational amplifier will become very high or go towards infinity. Okay. So, this is the standard procedure for synthesis of any of these control sources, whether it is starting from voltage controlled voltage source or current controlled current source or current controlled voltage source or voltage controlled current source. One must start with the corresponding idealized matrix, okay, and make the corresponding forward transfer parameter go towards a very high value or go towards infinity. Then that particular control source becomes that particular type of operational amplifier. It could become operational voltage amplifier or operational current amplifier or operational transconductance amplifier or operational trans resistance type of amplifier. These are the only 4 types of operational amplifiers that can exist. So, today we will see a specific structure which we have assembled. We said for taking care of the input impedance should go towards infinity or input conductance should go towards 0. That is done by the input stage, by proper selection of the input stage and its biasing current. Then the output resistance should go towards 0, output impedance should go towards 0. That is taken care of by selecting the proper stage for the output, that is common collector stage. And the very purpose of operational amplifier for operational purpose requires the forward parameter to go to a very high value. That is done by the intermediate stage. We could have obviously improved this GF further and decrease this further by cascading more stages, but that will complicate the stage in terms of causing the state to have more number of time constants, which will determine the open loop, okay, transfer parameter, and therefore then result in frequency instability problems when used under negative feedback situations. That is why we have frozen the number of stages to 3. Now, let us consider the input stage. We already have obtained this structure for a differential amplifier without using any resistors. So, this differential pair, in this particular case we have chosen it to be PNP transistor, assuming that in a technology, given technology, we have good PNP transistors available, we would select that. So, as to make the load, okay, load is now going to be decided by the NPN transistor, which is a current mirror. So, this is the active load, which is going to be the NPN current mirror. If we had chosen NPN input pair, then in turn we would have to go for PNP current sources or current mirror for the active load. So, this is one way we have chosen, primarily because the next stage is important in giving gain, and the next stage has to be necessarily NPN. Okay? And the next stage is going to be NPN, and it is going to have emitter connected to ground AC wise. That means emitter should be connected to minus Vs, and the potential here is going to be 1 diode above minus, okay? And therefore, we have naturally this acting as a suitable load without the need for any level shifting stage. Do you now understand why this configuration has been chosen? Okay? That is, the intermediate stage has got to be the high gain stage. Okay. The good NPN transistor will necessarily have high gain and good speed of operation, high frequency. So, this particular thing is going to have very high gain. That means, it is a common emitter stage here. Emitter is AC bias grounded, that means it is connected to the most negative potential for biasing purposes, and then from here you have one diode drop higher. Okay. If you select then the NPN active load, there will not be any need for what? Level shifting, which otherwise would have needed. So, this is a neat way of getting rid of the level shifting situation. Okay. But of course, we have to worry about getting good PNP as the input pair. That we will see how it can be achieved in practice, where NPN is given dominance, okay, and PNP transistors have poor beta. In such situations, right, we might have to see how to modify this further. In a situation where both good PNP and good NPN transistors are available, this can be straight away adopted. Okay. This synthesis can be straight away adopted. The final stage, the output stage, is nothing but the common collector, positive going signal being taken care of by the NPN and negative going signal being taken care of by PNP structure. Once again, in order that this performance of this, okay, composite structure should be good, we have to make NPN and PNP equally good. Once again, we have to see how in a given situation where no good PNP is available, how to modify the structure so as to make it as almost as good as the original NPN. Okay, that we will see later. But once again, we can say that when we have a technology where both NP and PNP are available, we can straight away adopt this simple structure as the basic structure for an operational amplifier. So, this kind of topology selection can be done even when we are told that the op amp to be designed should be coming out of a MOSFET structure, or it should be a BiMOS structure. We can then think of appropriate stages using appropriate transistors. For example, if you are asked to design the stage using BiMOS structures, then naturally input stage could be straight away MOS, because we can make this go towards 0 straight. The input stage can be straight away a MOS structure. Okay. The differential structure with this kind of active load using MOS, we know how to do it. Then the second structure will be retained as bipolar, because GM of a given bipolar for any operating current is going to be one order of magnitude definitely higher than that of the corresponding FET. So, this is going to be bipolar common emitter. Next one, good output stage with automatic short circuit protection could be a CMOS inverter itself. It will give you gain, okay, and can also act as a decent output stage, giving you almost the full swing possible, and it is automatically short circuit protected because, right, it is actually operating in the current saturation mode, and therefore, this is how we can come up with a sort of BiMOS op amp. Okay. Input MOSFET stage, intermediate bipolar stage, and output could be a CMOS inverter, right, stage.
But the output power CMOS
current, yeah. Most of
area ratio is,
yeah, most of these stages, all of these stages in fact have the same power ability. Okay. They are not basic stages, but what the one way to increase the power handling ability of these transistors is to merely change the geometry of the device, right. If you make identical geometry devices, they will all have equal power dissipation ability, right. So, basically these are not power op amps. We can even design power op amps if we make the output stage truly a power stage. Here output stage is merely used as a low output impedance source, that is all. Is this clear? Now, let us see some of the components that are coming here. We will discuss this part slightly later. This comes into picture for frequency compensation. This capacitor is internally put in internally compensated op amps. Otherwise, these two terminals are brought out in externally compensated op amps, wherein the user has to put suitable capacitor, okay, for its use. Load resistance can be connected externally. Now, the symbol for this op amp could be differential input, the dual power supplies and the output, all of this with reference to a common ground. Okay. So, output is available with reference to a common ground. We have op amps available with if V naught is A times, let us say A is the open loop gain, or right, that is actually GF. Okay. So, A times V1 minus V2, you have what are called as dual output op amps, differential input, differential output op amps, where you can also get minus A times V1 minus V2. Okay. That you can see in a differential structure that is already available. Okay. If one is A times V1 minus V2, the other one is minus A times V1 minus V2. So, in a suitable application, you can make it differential output, differential input. These are all the variations available to you. Now, obviously, you can notice this mode of biasing. This is a current mirror, okay, for obtaining low valued current. This we know. How we can obtain a current which is Vt log I1 by I2 divided by Re as equal to I2. Okay. If I1 is the current in this, I2 is the current in this, we know that I2 is going to be Vt log I1 by I2 divided by Re. So, given a circuit, you can quickly arrive at the value of the operating current here, because you know the value of Ra, you know, okay. In fact, this equation has to be solved. Okay. You can assume a value for I2 and get the value for I2. Okay. Iteratively you solve this and ultimately you will approach the correct value of I2. So, given the supply here plus Vs and minus Vs, the biasing current I1, okay, is going to be 2 Vs minus V gamma by R. Okay. The biasing current, main biasing current, okay, which is taken as the reference, is going to be 2 Vs minus V gamma by R. Now, you can, using this equation, you can solve for I2 and get the value of I2. In a typical situation, this will be of the order of tens of kilo ohms, okay, and this current is going to be of the order of milliampere, okay, and this current is going to be of the order of few microamperes. Okay. And typically, therefore, the input resistance of this, which is going to be beta plus 1 times 2 Ra, okay, is going to be of the order of mega ohm or so. Why? mainly because you are operating at current of the order of microamperes. Okay. Re being equal to Vt by I2 by 2, right. So, you can evaluate the input impedance of this stage. It has been made on the open loop to be of the order of mega ohms typically. So, then what else? Gain. When Vi is applied here, Vi by 2 Re is the change in current superimposed over and above. Let us see, draw that. This is going to be I2 by 2 and this is going to be I2 by 2. Okay. And we will have, okay, this current, if it is increasing by some amount, this will decrease by the same amount. So, if we have this as, let us say, plus delta I, this will be minus delta I, and we will have this as I2 by 2 minus delta I. And we see here that we have a current of 2 delta I being pumped into this. This under the situation that all these things are behaving like ideal current sources or sinks. Obviously, right, what it simply means this is that this stage is taking away the entire signal current. That is not the case. Actually speaking, what happens is there will be finite impedance here due to this, okay, and the input impedance, okay, that is going to effectively act as the load and voltage will be developed. Here it is shown as though it is 2 delta I times the input impedance of the next stage, right. That is primarily because we have ignored the output impedance of these current sources and sinks. Okay. So, under the situation that most of the current is going into this, right, the current that is coming here is going to be, this is base current. So, if you ignore the capacitor, this is going to be beta times that current, okay, and that has to develop an output voltage here. Once again, the load here in the absence of RL, if RL is infinity, is going to be determined by primarily the output impedance of this current source. Okay. If you put an RL here, then you have to consider the effect of RL here, which is nothing but beta plus 1 times RL here appearing, shunting this output impedance. Now, at every point you see the need for knowing clearly what the impedance levels are. Okay. This impedance has to be pretty high, so that the gain, which is nothing but beta times 2 delta I into whatever impedance is seen there, which is nothing but beta plus 1 times R, okay, shunted by the output impedance of this, okay, is made as large as possible. Now, what is the operating current of this? How do you find out the gain of this stage, right? If you, okay, if you are told that these are not given in terms of currents, but I give the impedance levels here, impedance level here, and you can find out the impedance level here because the operating current of this is known. If this is 2 Vs minus V gamma by R, if this is a current mirror, the same current will flow through this, okay, and therefore, you know the Re of this, and the gain of this is going to be nothing but the impedance at the collector divided by Re of this, right. So, obviously, this is going to operate at higher current than any of these. Re has to be made low, but when you make Re low, you have to be aware of the fact that, okay, it is going to load this also, the impedance level here comes down. So, naturally, we have to see that the impedance level here does not come down. So, we have to increase the beta, right. One way to increase the beta is to use a Darlington pair. Okay. So, these are all the modifications that might have to be adopted here. Okay. Here again, we can increase the impedance level by putting emitter degeneration resistors, okay, or using Wilson current mirrors. Okay. So, we can improve the gain of this whole thing by adopting proper techniques, but given a situation now we are able to obtain the open loop gain of this stage, right. What is the open loop gain of this particular stage? 2 delta I into beta into the effective collector resistance at this point, that is the DC open loop gain, DC. So, I know the input impedance, okay. So, I know this parameter, okay, 1 over that input resistance, okay. I know the open loop gain, that means I know GF, right. Now, how do I evaluate the output impedance? Now, this is not very easy, because you are saying this is going to be class B, right. Operating current is 0, okay. So, you have to assume some class AB biasing, that is ultimately we will see that this is not class B at all, it is made class AB. So, there is going to be some amount of current in this, okay. So, you can evaluate the value of RE at that particular point. Most of the time the output impedance is going to be governed by this, okay, plus this divided by beta, okay. The impedance level here being high, okay, the output impedance of this is rather governed by mostly this divided by beta plus 1, okay. Apart from that, you have to also take into account, if you are likely to put, this is an output stage, therefore, it will require short circuit protection automatically, and again the same scheme of current sensing resistors have to be put here in order to divert the drive. This we will bring in later slightly, okay, the protection scheme, but it is exactly similar to what we had discussed for the voltage regulator. So, there will be series resistances coming in series with these emitters, and they will naturally come as additional output resistances, okay. So, next, what about the common mode swing as far as this is concerned? We have now evaluated all these parameters. This is for all practical purposes 0, okay. So, we know the way to evaluate the actual G parameters of a given operational amplifier given the configuration. Now, let us see something about large signal effect. As far as the common mode signal is concerned, we are going to connect this together, and then the common mode voltage can vary as much as 1 diode drop here, this can come up to this, no problem, and there is one more diode drop. So, 2 diode drop less than Vs, that is the maximum limit of common mode voltage. Here, as far as minimum is concerned, let us see, swings 1 diode drop, okay, higher than minus Vs. So, you can straight away see that it has the maximum common mode signal swing desired, okay, so as to prevent any what? Why do you want this kind of common mode swing? Latch a problem when you use it again in negative feedback situation. Okay. So, this stage has been therefore well chosen, okay, and that is why very few changes have taken place over the years, okay, as to the topology of the configuration that is going to act as input stage. Okay. Then as far as the output is concerned, once again you can see output can swing, that means 2 diode drops less than Vs, and once again let us come here. Okay. So, 1 diode drop collector, 2 diode drops higher than minus Vs, which is in conformity with what is happening for the common mode voltage almost at the input. Okay. Now, that is as much for the large signal effect. Now, we will come to the most important point about operational amplifier. So, I want to now talk about two important parameters associated with op amp. One is bandwidth, okay, need for frequency compensation, and the second one is slew rate, which is a large signal parameter. First one is a small signal parameter, bandwidth. And then slew rate. So, let us see what is the need for frequency compensation. Briefly, I would like to touch upon, so that most of these op amps are likely to be used in a negative feedback situation. Let us see what. In this particular case, it is a voltage amplifier, and therefore, its open loop gain is going to be, let us say, A naught divided by, how many stages are there? 3 stages. So, there are likely to be 4 time constants. Okay. So, 1 plus S by omega 1 to 1 plus S by omega 2, 1 plus S by omega 3, if this is the first corner frequency, this is the second one, this is the third one, this is the farthest one. In practice, okay, for a general purpose op amp like 741 or 747, the first corner frequency occurs, okay, at about 1 megahertz. F1 is going to be around 1 megahertz. So, what it means is that if you plot the gain, this is going to be almost flat up to 1 megahertz, then it will start falling at 6 dB per octave or 20 decibels per decade, and then it will start. Okay, this is going to be F1, this is going to be F2, this is going to be F3, and maybe F4 is out of by the time F4 comes to picture, right, the gain has become less than 1. Okay. So, in the useful range where the gain is greater than 1, okay, it seems only this F1, F2 and F3 come into picture. Okay. Magnitude of A naught, A. Magnitude of A versus frequency. So, that means strictly speaking, you have a possible gain of something like 10 to power 5 to 10 to power 6, that is the order of open loop gain, typical order of open loop gain for most of these common operational amplifiers, bipolar, 10 to power 5 to 10 to power 6, and a bandwidth of about 1 megahertz. Strictly speaking, you should have, okay, a gain bandwidth product of 10 to power 6 megahertz, 10 to power 5 to 10 to power 6 megahertz. But you are not able to use this band. Okay. That is because there is a cluster of these poles influencing the phase shift over the frequency range. So, that means even when the gain is high, greater than 1, okay, this has already come into picture and causes the gain to have a phase variation with respect to frequency. This next comes into picture. Right. So, obviously somewhere in between now, what is the phase shift at this point, if only due to this, not due to other things? At the corner frequency it is going to be 45 degrees, right. At the corner frequency, if the other poles are not influencing, it is going to be 45, because j omega 1 you will put 1 plus j. So, it is going to be 45 degrees here. By the time you go out of this, assuming that this is now contributing more of its phase shift and already has contributed enough, okay, totally giving a phase shift of 90 degrees. So, when the next comes, let us say, this will contribute 45. So, you have 135 here, right. It may be more if these are very close to one another. If they are farther away from one another, this is likely to be 135. So, it is 135 or more here, right. Obviously, in a frequency range between this and this, it is likely when they are staggered far apart only, otherwise it can come anywhere here also. The phase shift can become equal to 180 degree, then it will start oscillating in that negative feedback situation, right. So, if the loop gain, that is A into beta, is still greater than 1, then there is a possibility of it oscillating. If A into beta, beta is the feedback factor, okay, is less than 1, when this 180 degree phase shift occurs, it is not going to oscillate. For all values of beta, if it is to work, then the worst case value for beta is 1. Okay. So, a general purpose op amp is designed okay, for making this A become less than 1 when the phase shift of the entire thing becomes equal to 180 degree. That is done artificially by shifting these poles, okay, one of these poles to this side, artificially cutting down the gain. So, if you cut down the gain, what happens? The gain starts falling much earlier, and then by the time this first pole comes into picture, the gain has been made less than 1. Okay. That is what is called as dominant pole compensation, which is universally adopted for most of the internally compensated op amps. So, that anybody using it, okay, it will never give trouble. There is enough margin of safety, so that it works even if there is additional phase shift given by the beta determining network itself, okay, offers some additional phase shift, still it is not going to be unstable. So, for this eventuality, you cut down this gain. So, you can see that actually speaking, this particular amplifier has lost most of its useful bandwidth simply in order to make everybody use it in all sorts of negative feedback configuration. Suppose therefore, you are designing your own amplifier for a specific gain, then there is no need for so much of a margin. Okay. That is why the manufacturers also have given the same configuration almost without the internal capacitor being connected, with a provision for you to connect it, so as to increase the frequency of usage of that. Okay. But however, in this case, they would like to put as small a capacitor as possible inside for compensation, because we know the capacitor takes lot of area within the IC chip. So, the basic idea behind compensation inside is always this, that the capacitor should be always connected to 2 high impedance points if they are available. Okay. Why? Because I told you the time constant that determines, okay, the cutoff frequency always depends upon the capacitor into the net resistance across the capacitor. Okay. That is the time constant which determines the reduction in gain. So, obviously, you should connect it to 2 high impedance points. Now, the two high impedance points available straight away for you inside the structure are this one and this one. Okay. Those high impedance points should have obviously the signal phase shift of 180 degrees, so that the connected capacitor will result in negative feedback. Okay. So, this capacitor comes into picture as what is called Miller capacitor, that is another way of looking at the thing, right. Because you are connecting it between two high impedance points, okay, at the input it will come as a huge value of capacitance. So, that means essentially now we can consider that this is the time constant which determines the gain reduction. Okay. So, effectively these time constants are all going to be replaced by this particular time constant, and it is enough if we discuss most of the op amp application only using a simple model for the op amp which says A is equal to A naught divided by 1 plus S by omega dominant. That is called single pole roll off characteristic, dominant pole, okay, which is created by the compensating capacitor. Now, essentially this frequency comes pretty close to 0. Typically it is of the order of few hertz. Okay. That means in most of the applications of the op amp, right, which is much greater than hertz, okay, you can consider that op amp gain is A naught divided by, that means the op amp itself is acting like, right, an integrator, right. In its transfer function you can see it is acting like an integrator, or what is this, equal to A naught into omega d by S. This is called gain into bandwidth. Okay. So, this is called A naught into omega d is called an important parameter which is gain bandwidth product of the op amp, which is a measure of the quality of the op amp, up to what frequency it can be used, etc., with what value of gain. Okay. So, this is a measure of the quality of the op amp, an important parameter, small signal parameter. So, let us now see how this can be roughly estimated from the internal structure. That is what we are interested in finding out. Let us once again come to this. This is V2, V1, and this is Vi. So, if we have Vi, the current in this is going to be, let us say, I2 by 2, I2 by 2, okay, and this is minus delta I, this is going to be plus delta I, and now you can see that delta I is going to be 2 delta I is going to pump into this. Now, I can replace this whole thing only for signal picture as an amplifier, op amp itself. This is grounded, okay, and you have a situation of an amplifier with very high gain, because most of the gain of the amplifier is concentrated here, neither here nor there, right. So, this 2 delta I is going to now flow through the capacitor because of the Miller effect anyway, right. So, very little current goes through this and most of it goes through the capacitor and develops a potential which is 2 delta I divided by SC. Okay. Is this clear? With this n minus and this n plus, and this potential is already at nearly ground potential, okay, because this is a high gain stage, right. So, by just replacing delta I, what is delta I in this particular case? Is equal to 2 delta I. Delta I is equal to Vi by 2 Re into S. Is this clear? You might be wondering at this approximation, because this is a similar approximation as in here. If you do not make the approximation, you would have got the gain as A naught by 1 plus S by omega d, that is all. Okay? What is that? If you have considered all these impedances and then consider the Miller effect capacitor shunting it, then you would have got the output as A naught by 1 plus S by omega t. We are not interested in all these things, we want only the gain bandwidth product. So, straight away we can go for the approximation and we see that gain bandwidth product of the op amp is equal to, how much is that? Re into 1 over, that is Gb is equal to 1 over Re into C. What is Re? Vt, okay, divided by I2 by 2. Now, we know the designer knows the operating current of this transistor. It is of the order of microamperes. C you put of the order of picofarads. Vt already you know. Then if you do this, you will get gain bandwidth product. This is actually omega. You have to convert it into F. Okay. So, 1 over 2 pi you have to make. Then it will be of the order of megahertz. Okay. Automatically get it as. So, please work it out for a typical situation where I2 is of the order of microamperes and C is of the order of picofarads. Okay. Vt is known 25 millivolts. Okay. This is going to give you omega. So, if you convert it to F, you will get it as order of 1 megahertz, which is typically what it is for 741 type of op amps. Now, you know how you can manipulate the gain bandwidth product based on bias current and compensating capacitor. So, given the configuration, you immediately can now tell about the gain bandwidth product of the op amp. You should be able to, right. Is this clear? Now, just this is a small signal parameter. Exactly in a similar manner, we can argue something for the large signal parameter. Please follow me very carefully here. After a certain point of time, we can no longer say delta I is okay, Vi by 2 Ra. It is nonlinear. We can only say that Vi delta I depends upon Vi. It is nonlinear. So, we are going into that region where okay, delta I is nonlinearly dependent on Vi. We are not bothered about that. What happens as Vi increases is delta I goes closer to I naught by 2. At that point of time, when delta I becomes equal to I2 by 2, this transistor is off. This transistor is being given the total current. Thereafter, further increase in Vi is not going to change anything as far as the circuit is concerned. So, this will pump a current of I2 into this. When a DC current of I2 is pumped into a capacitor, the current of I2 is getting pumped into a capacitor, what will be the voltage? I2 by C into T. DC current I2 getting pumped into the capacitor, voltage across the capacitor is okay, 1 over C integral I dt. So, I2 is a constant. So, I2 by C into T. That means, after this the op amp gives up, says look, you are demanding too much from me, right. I cannot increase at a rate higher than the rate which is I 2 by C. What is this is equal to nothing but V naught, right. But the gain of this stage is unity, right. So, d V naught by dt max is nothing but I 2 by C, and that is defined by the manufacturer as slew rate. This is an important parameter of the op amp which every user must understand thoroughly before using it in any application. Okay. Actually, this is grossly misunderstood most of the time. That is why I am insisting that you should understand this very well. This is the highest rate at which output is capable of rising. If you demand higher rate than this of the op amp, output will rise at slew rate. Okay. So, this is not dependent upon actual value of the signal, but depends upon the rate at which voltage rises, and this happens normally if it is a sine wave that you are expecting at the output when zero crossing occurs. So, this distortion starts occurring not at the highest signal level, but at the lowest signal level where the zero crossing occurs, where the rate is the highest for a sinusoid. So, you will see that if you are expecting a sinusoidal output at the output of the op amp, and if you are demanding higher rate than the slew rate, the sine wave starts getting distorted, gradually transforms itself at around 0 into a triangular waveform, unlike other distortions which are mostly signal level dependent distortions. This is rate dependent distortion. So, I 2 by C, and you can again find out what the value of this is going to be. I 2 is of the order of microamperes and C is of the order of picofarads, and therefore, typical slew rate is of the order of volts per microsecond. Typical slew rate of this is of the order of volts per microsecond, 741 like op amps. So, with these properties well understood, we can actually analyze any given IC and see what its small signal and large signal parameters are. Also, given the task of designing a specific IC, we can attribute specific values for the various components within the IC. Thank you.